Okay, and sharing my slides here. Okay. Okay, let's wait for another minute, then we're gonna get started. All right. So today I'm gonna try to finish the chapter number 5, and if we have some time left, so we can talk about the previous practice assignments. So have you had chance to practice those R code? Okay, cool. Yeah, that's good. All right, so let's get started. Let me stop my video here. Okay, so I think last time Adrian asked a good question. So he asked why we need to define this variables, right? The mu is the midpoint, A is so-called additive effect, and the D is the dominance effect. So why do we need these terms? Actually, this is for our own convenience, because so probably most of you have already heard about like the GWAS, right? GWAS means like if you have a population, either the breeding population like the backcross or F2 population, or even you have a natural collection. So, for example, human population. Excuse me. All right, so once you collect the data, the genomic data and the phenotypic data, so for example, this is the genome for each individual, and we have like a lot of like SNPs, DNA variants, right, along the genome. For example, here, 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 and here. As we know, not all of these SNPs or DNA variants are responsible for the variability of the observed phenotypes. Only some of them, either the major loci or the minor loci. So we need to find out, we need to detect those loci, the quantitative traits associated loci, right? So this is one of the topic we would like to cover in this class. All right. So when we want to test each of these loci, we need to know what we can test, right? So this is how and why we need to define these terms here. So for example, if we want to test if this loci, this locus is significantly associated with the trait of interest, then if this is the locus, then it could be like some genotypes will have like additive effects, and some genotype will have both additive and the dominance. And once we have these terms, we can estimate. So now we will go back to our business, right? So if we assume there's an effect, and then we can use our data, the population data, to estimate this additive effects or the dominance effect for this locus. Then we can do the test. So I hope you still remember what we do in the hypothesis testing, right? So suppose we want to test this loci, whether the additive effects equals to 0, or whether the dominance effect equals to 0. So this is our non-hypothesis, right? Of course, the alternative hypothesis means like A is not equal to 0, this not equal to 0, or A equals to 0, but D, A is not equal to 0, but D is equal to 0, something like this. Okay, we can test this. What does that mean? That means like if we the based on the data for this locus, if we got like everything is 0, means yeah, there's no effects at this locus that is related to the phenotype, phenotypic variation. So then we're gonna ignore this locus, right? So we're gonna keep scanning the genome until we find some like significant signal. So this is something probably in the publication, you're gonna see something like the Manhattan plot. So this is the signal or test statistics, and this is the chromosome or genome. And you're gonna see like majority of the signal is very low. So that's the noise, something like the non-hypothesis, there's no signal. But for some loci, you're gonna see like this, right? And this, and this, and this. So what does that mean? So in the future, so after you finish this class, so next time when you read articles, if you see this kind of like Manhattan plot, this plot actually shows the continuous test along the genome to find the loci that are associated, responsible for the traits. So this is the signal showing, okay, some genes in this region will be responsible for the traits. The same thing here. So this is what we're gonna do here. So how do we do that? So we need, for each potential locus, we need to define this, right? And once we can estimate this, then we can test if these effects are 0 or not. And the non-zero effect at any locus means this is a QTL. This is a quantitative traits loci, and this is what we want to find from the genome. Does that make sense? Okay, good. All right. So very important here, we need to understand from here. So this is the observed phenotype for each individual, right? Each individual has, so in this case, we are talking about they have 2 design probably. So for each individual, there are 3 possible genotypes at a single locus. So we are talking about a single locus. But once you understand this, you can easily extend this to any loci along the genome, right? You do the same thing. You do the test for each locus, scan the genome and find an association, potential association between the genomic loci and the traits. Okay, so this is the observed phenotype, and this, the average means like the G11 means the expected or average phenotypic value for this genotype. So we're talking about 11 means like A1, something like this. Okay, then, yeah, based on this expected phenotypic value, sorry, then we can easily define the midpoint, additive effects, and the dominance effects. So we use this diagram to help us understand this. All right, so this is the phenotypic value for A1. Okay, and this is for the A2 and the A2, right? And this is, of course, the heterozygous. So we define the difference between A1 and A2 as 2A. And the deviation from the heterozygous phenotypic value from the midpoint is the dominance effect. So this is how we define this. And so pay attention. So once we have the data, we're going to estimate this value and this value, and we're going to test if these values are 0 or not. So this value, non-zero value of those 2 effects reflect the association between this locus and the traits. And the larger this effects, the strong signal or strong association between this gene, this locus, and the traits. Any questions here? Okay. So last time we very briefly mentioned how we can calculate expected value or mean for a random variable. So this is the formula, right? So if we want to calculate the expected value for the x, let's say x is the possible outcome from this experiment. So when we roll a dice, there are 6 possible outcomes with equal chance. So that's why you see everyone has this probability. And the formula of the expected value for a random variable equals to the summation. So this is the general term of each possible outcome, xi. So here, xi equals to, could be 1, 2, and 3, and 4, right? So the summation of each outcome multiplied by its probability, right? This is a simple case. So suppose this is not a failed die, and if some numbers are if some numbers have a higher probability to show up, then this formula will not look like this, right? So you still see the 1, 2, 3, 4, 5, and 6, the 6 possible outcomes, but you need to use different numbers here, probabilities, because they're not equal chance. So you have to know the probabilities that are associated with each possible outcomes and use that number to do the calculation. Then in that case, you're gonna see a different number from here, right? Any questions here? So this is important because later on, we're gonna use this a lot to help us calculate the genetic effects for any allele or genes in a population. So, and once we are comfortable with this in the future, you can use you can repeatedly use this test along the genome to perform a genome-wide association study, GWAS, and try to find the loci, the genomic loci that are responsible for the trait variation, the phenotypic variation. Okay, so important. All right, so this is an example showing like the two outcomes have unequal probability, right? So if you play this game, like the Renate game, as you can see, the expected value is negative, means like you always lose money if you go to Las Vegas. So the reason why is that because we have like two outcomes, right? One is the lose each time if you bet incorrectly, so you lose $1. Small amount, but yeah, probably you don't pay much attention. You do not pay a lot of attention on this, but probably people pay more attention on this. So once you bet the correct number, you're gonna get this much. So that's a lot. But these two outcomes have different probability. So the chance of winning this number is only this small. 1 out of 38, but you have much more chance to lose this $1. So in a long run, so the expectation actually is a measure of the either the winning or the losing in a long run. So as you can see, if you bet a lot of times, so generally you're going to lose money. That's the expected value. So using this example, I just want to show you how you calculate the expected value for a random variable, right? So again, this is the formula. Don't forget about this. It's the summation of any possible outcomes that and the associated probability. You have to do this, right? Just like this. Okay. All right. Okay, there's another important statistic we need to pay attention. So once you want to describe a population or random variable, usually there are two things you need to pay attention. One is the expected value, which is the mean of the random variable or population, right? So this is some like measure of the central tendency. So usually you want to see like what is the center of the distribution or the random variable, right? That's the center measure of the central tendency. There's another one is called the variance. The variance is another thing to describe this population or a random variable. So to definitively define a distribution or a random variable, we need to know the central tendency, and we need to how widely this distribution is spread out, right? So the variance is actually a measure of the spread of the distribution. This is another important. So if you compare two normal distribution, one is like this, the other one is like this. So if you look the center of these two distribution, they are the same. They're all centered around this value, let's say 0. But do you think these two distributions are identical? No, because these two distributions have a different feature in terms of the spread, right? So the yellow one has a large variance, and the pink one has the smaller variance. So remember, when you want to describe a distribution, you have to consider the central tendency, which is the expected value, and the variance, which is the measure of the spread. Okay, so this is the definition for the variance. The variance is actually also the expected value, but the expected value of what? So this is the central tendency mean, right? The expected value of the random variable itself. But when we calculate the variance, so this is the expectation of the squared value of the deviation from each random variable from its center. Does that make sense? So we want to calculate the expected value of the squared value of the deviation from each outcome from its center. It's kind of like complicated, but I hope you can follow this and understand what is measuring here. And this is the formula. So in the test, I will give you some problems, and you need to use this formula to calculate the variance of X. But don't worry, sometimes like if you do not remember this, in the final exam, I'm going to provide these formulas for you. But you need to know how to use this formula to calculate the variance for a random variable. Okay. Okay. So I just took this from the website, Google, and the same. So this show you how to use different formula to calculate the mean and variance here. Okay. Okay. Now, so the previous like several slides are the fundamental knowledge in terms of statistics, right? So you have learned this in your statistics class. Now we need to know how we apply those expectation and the variance calculation in our business. So here we want to find out the feature. So here the feature means what? Means the additive effects or the dominance effects for any locus. Let's say a single locus here. We use this is a F2 population, right? We use this to represent the genotypes, 3 genotypes of this locus. And we want to study the feature of this, the feature of these 2 effects within this population regarding this locus. All right. So we can study this, and we can do the same thing for another locus. For example, there's another locus. We use B1 to represent this B1 B2, and so on, to represent another locus. And we can do the same thing for the other locus, right? So here it is very generalized situation. So now we talk about just one single locus now, and for this locus, So we are comfortable with this, right? This is the sorry, the expected phenotypic value for genotype A1, A1. And we define the genotypic value for A1, A1. So this is the phenotypic value, the expected phenotypic value. Now we define 511 means the genotypic value for this genotype A1, A1, which is the difference or deviation from the phenotypic value, of the phenotypic value from the midpoint. So we actually calculate the difference between the phenotypic value and the midpoint. So the same thing. So if we want to calculate the genotypic value for A2, A2, this is equal to the difference between the phenotypic value of A2, A2 and the midpoint. So the same, right? The genotypic value for the heterozygous individual will be the difference between the phenotypic value of this A1, A2 and the midpoint. So if you have learned the normalization term in statistics, so this is the same. So actually, the genotypic value is the normalized phenotypic value around the midpoint. Can you follow this? Yeah, we just put everything on the same scale. So we compare every phenotypic value with the midpoint, and the deviation or the difference between them is defined as the genotypic value. This normalization process is totally like for the convenience of our calculation. So once you are in the future, once you are very familiar with the bioinformatics, so once you analyze a high throughput data set like the gene expression, the RNA-seq or something like that, so usually you are going to deal with the normalized data. You're going to normalize the data with some general mean, such that you can make your calculation a little bit easier. So this is the same. This is the same thing we want to do here. Make the computation a little bit easier. Any questions? So here it's very confusing. So I highly recommend that before you come to my class, if you have time, please read the textbook, because textbook is very clearly described. Because due to the limited time in the class, I cannot cover everything. But if you can read the textbook earlier, so it will be easier for you to follow my slides here. Yeah, I try to put everything in a logic way and introduce them to you clearly. But as I mentioned, due to the time limit, so I cannot cover everything. It would be beneficial for you to read the textbook beforehand. Okay, so this is important. So I hope you understand the difference between the phenotypic value and the genotypic value. So the genotypic value is actually a normalized phenotypic value. All right, so suppose, so this is a F2, right? F2 population, and suppose this loci is following the Hardy-Weinberg equilibrium. Okay, there's no other like outside external evolutionary force. All right, the population mean here, we're talking about the population mean of genotypic value. So we're talking about this now, the 5 value here. So see, this is how we calculate the expected value, right? We calculated, we want to calculate the expected value for this guy, the genotypic value. Then we use the formula I just told you, right? This is the formula, like summation of each possible outcomes multiplied by its probability and do the summation right here. So here we have I from 1 to 3 because we only have like 3 genotypes, right? And this is what? The P11. Can anyone tell me what is the P11 here? The P11 is actually the probability of this genotype, right? So last time we talked about this. That's the P11. So why is that? Because this is the genotypic value for the first genotype, A1 and A1. So if we want to calculate the average or expectation of this phi, so we need to make the summation of all these possible outcomes. This is the possible outcomes for this phi, right? Multiplied by its associated probability. Is that clear? And so in the final exam, probably I will let you to tell me how to calculate this expected genotypic value for a population. So you need to know this formula. Okay, now, and because we knew from last time, we knew this probability. So if this loci is following the Hardy-Weinberg, right? And this probability equals to P1 squared, right? This probability equals to P2 squared. The P1 and P2 means what? Means the allele frequency, right? The A1 allele frequency. And this is the probability for this heterozygous genotype, the probability. Either P1, P2 means like either you got, so the individual got a allele from mother, but B allele, A1 allele from mother and A2 from father, or the other way. It could be like A1 from father and A2 from mother. Either way can end up with the same genotype. So that's why we need to multiply 2 here. So that's the probability for the heterozygous genotype. All right. So once you got this and this, so this is the genotypic value is A, right? And for this one is minus A. So this is why so this is how we understand this formula. And for the genotypic value for the heterozygous individual, that's the D, right? Excuse me. Okay. Any questions here? All right, so this is important. So this is how we calculate the population mean in terms of the genotypic value. And we also want to calculate the genetic variance, which is the variance of the genotypic value. So we knew the formula, right? And then we need to just calculate these 2 terms and take the difference. So this one means like the expected value squared, just like this. This is the expected value. And if you put everything in the parentheses and square it, that's the term here. Pay attention, notice the difference of these 2 expression, okay? So this means like the expected value of this squared, but this is the expected value of this thing squared. So this is the same, following the same formula. If you want to calculate the expected value of the genotypic value squared, you need to make a summation of all possible outcomes. So here, the all possible outcome is like this. So the first possible outcome is the genotypic value of A1 squared. The second is the A1 A2 genotypic value of A1 A2 squared and squared here. I assume everybody are comfortable with this because this is very basic statistical theorem. If you do not feel comfortable with this, please, when after class, please find some like a statistical book, basic one, or even online, you just search the variance, how to calculate the variance of a variable. Then this will help you understand this, and this is important. I hope everyone knows how to calculate the expected value and the variance if I give you a random variable. So definitely, I'm going to put something in the final exam. Okay. So before you calculate the variance of the genotypic value for a population, right? First, you need to calculate the expected value for the genotypic value. And then, so if you have everything, you can easily prove if this loci is under the Hardy-Weinberg if this is a F2 design, so we can easily prove the variance of the genotypic value at this locus equals to this. Any questions here?
No question.
Okay, perfect. Thank you for letting me know. Okay, let's move on. All right, so today, I'm sorry, I have to give you a lot of like confusing terms, concepts. Please, yeah, if there's a, so definitely when I remember when I first take this class, and this is the most confusing parts because there's a lot of like new concepts and they are related. So if you cannot like fully understand each of them, the difference between them in the class, yeah, please make sure you understand the difference between them after class, because this is very important. Otherwise, yeah, in the future for the following like study, so it will cause a lot of confusion if you don't resolve the confusion here. Right. So in the first few slides, so the major confusion is like you need to understand the difference between this phenotypic value and the genotypic value. The genotypic value is actually the normalized phenotypic value. So normalized by what? By the midpoint. So that's why we just minus everything by this mu, right? The midpoint. So this is one thing you need to pay attention. And now, so the average effect of an allele is the mean or expected deviation from the population mean. Population mean is the expected of this, right? We use mu to represent that. Mu g, sorry, not mu. Mu without g means the midpoint, but mu g means the expected genotypic value. So this is another confusing. So we maybe in the future, for the next edition of this book, so we need to use some other notation for the midpoint. But unfortunately here in this book, we use the same mu to represent different things. But mu without anything is the midpoint. If you see the mu g, which is the expected genotypic value for this locus, so hopefully, so that's why you see. Let's see. So mu g here, right? This is not the midpoint anymore. This is the expected value of the genotypic value. Okay, a little bit confusing here. So the average effect of a allele is the mean or expected deviation from the population mean of any individual which already received that allele from one parent, but the other allele can be randomly chosen from the population. What does that mean? That means like, so why we need this? So this is totally like useful, very useful in the breeding. So suppose you have a parents of a genotype A1, right? And these parents can only produce gametes with A1 allele. Then, so this is why we want to calculate the average effect of an allele, because if this gamete will come together with any gametes randomly chosen from the population, either so here we just talk about the biallelic population. So for this locus, we only consider like two allele, right? One A1 and A2. This parents can only produce this allele, and this allele has two possible outcomes, right? If this allele come together with a A1, which is randomly chosen from the population, then it will form a genotype like this. Oh, sorry, A1. If this allele come together with the A2, which is randomly chosen from the population, then it will form a genotype like this. So there's two possible possibilities. Then since it's not definitive, so we have to calculate the average or expected genotypic value from this allele, right? So this average effect of this allele represent the breeding power for these parents, because these parents will only produce the A1 allele. And what is the breeding power for these parents? So we use the average effect of the allele, this allele, to represent the breeding power. So since this parent has two A1, right? The breeding power, so we're going to talk about this later. So the breeding power, or we call the breeding value for this individual, will be the 2 times the average effect of allele A1. Does that make sense? So this is the breeding value for this parents. And of course, for a parent which has A2 and A2, we can also calculate the breeding power for this parents, right? Which means, so the breeding value or breeding power for this parents will be 2 times the average effect of the allele for A2. Does that make sense? And the same for A1, A2 parents. So we can easily use this average effect of any allele to represent the breeding power or breeding value for any parents. So this is a very simple situation because we only consider 2 alleles, the biallelic population. This can be easily expanded to the loci, which has more than 2 alleles. Does that make sense? I hope, yeah, I explained this clearly, because the reason why we want to calculate this, because we want to use these values to evaluate the breeding power for any parents of specific genotypes in a breeding program. Does that make sense to you? Okay. So now, suppose alpha 1, this is alpha 1, okay? Confusion, not the additive effects. This is the alpha 1. We use alpha 1 to represent the effect, the average effect of allele A1. Since this is the expected, right? The expected deviation from the population mean, then we still use this expected value, the formula, which is the summation of any possible outcome multiplied by its probability. We still use that. We keep using the same formula here. Sorry. So this is the alpha 1, which is called the so for simplicity, we can just think about this. Let's look at this term first. This is like the first is the genotypic value of A1 from the population mean. So this is the population mean, deviation from the population mean for genotype A1 and A1, right? So can you follow me? So this is important. This is defined as this. All right. And since we're talking about A1, and why is that? Because you already have a A1 from parents, right? Then there are 2 possible outcomes to form a gametes by using this first selected A1. Either this A1 will come together with another A1, which is randomly chosen from the population. So I use this to represent the random. Or you can randomly choose another allele from the population to come together with this first chosen A1, right? There are 2 possible outcomes. That's why you see the 2 things here, right? And what's the probability to form this A1, given you already have an A1 from the parents to be evaluated? You just need to choose A1 from the population, right? Can you follow me? Yeah, that's the probability. That probability equals to P1. Does that make sense? The allele. All right. So if this is the case, then you simply simplify this. So this is why we multiply the deviation of the genotypic value of A1 from the population mean multiplied by its probability, which is P1. Does that make sense? That makes sense, right? Okay.
I'm actually a little confused. Can you repeat that one more time?
I'm sorry. Repeat this, right?
Yeah, repeat it, please.
Okay, sure. All right. So I think yeah, this is a little bit complicated. Let me simplify this first. So we rewrite this into this. Okay. So the first part is this. Yeah, it's too complicated. I'm gonna use this part, okay? And multiply it by P1. Can you follow me? And the plus, use another color. So this term represents this term, the deviation multiplied by P2. So why is that? So can you follow me? So I just simplified this equation to this.
Yeah,
And
okay,
good. All right. So this, for this one, why the associated probability is P1? Because this is conditional probability. We already get a A1. So we want to evaluate this A1, right? The average effect for this allele A1 from one parent. So this A1 can form two possible zygote if we give another, if we randomly choose another allele from the population so if we randomly choose another allele from the population and give that allele to this A1, it can form a zygote, right? So there are two possible ways. Either you randomly choose a A1 from the population, which the probability for which the probability will be P1, right? Or you can choose a, well, this color is not good, sorry. Let's use this. So you can easily select a A1 randomly from the population with the probability equals to P1. I hope this is clear. And another possible way is like you choose a A2 allele from the randomly from the population with the probability equals to P2, right? All right, so there are two possible ways. Then, so the outcome from this is what? You can form a individual progeny with genotype like this. The conditional probability is P1. Does that make sense? And the second outcome is like using the same allele from this parent, you can form another genotype is A2, but this time you have the conditional probability equals to P2. Does that make sense?
that makes more sense. Thank you.
Oh, good, very good. Then, so since you knew you have this, it's straight. It will be straightforward for us. Let me use this to calculate the expected value using this summation xi pi, right? So this is how we calculate the expected genotypic value for this A1 allele. So I hope, yeah, I made it clear here. And so this is the formula provided in the book, but I just go further to simplify this to help you better understand this. So this is the breeding power or breeding value for a single allele, A1. Okay, and we can follow the same logic to calculate the breeding value or breeding power for A2. So A2 can have two genotypes, right? Either if you already have a A2 selected from the parents of interest, and what is the breeding power for this A2 allele? So this A2 allele can be combined to any alleles selected from the population randomly to form two genotypes, right? So the first genotype is A2. You got another A2 from the population. And the second one is A1, right? If you got another A1 from the population with the probability equals to P1 or P2, right? The same. Okay, then this is how we define. I would like to say this is the breeding power or breeding average breeding power or the average or the expected genotypic value provided by this allele, single allele. All right. And okay, so if we add this, so for example, if we have one allele A1 and another allele A1, so if we add up these two alpha 1, that's the breeding value for this. And because, so in this table, so there's another thing called the dominance deviation, which means like when you look at the difference, the deviation between the genotypic value for this genotype with the population mean, it equals to actually, for this genotype A1 and A1, it equals to the average effect for this A1 plus another average effect for this A1 plus a difference deviation. So this deviation is something that cannot be explained using the linear model, because this deviation, dominance deviation, we call this dominance deviation as the interaction between potential, the interaction between the A1 allele and A2 allele within the population, which is a non-linear feature. So this non-linear feature cannot be simply captured by the simple linear model, unless we use more advanced model, for example, like the polynomial or higher order of the linear combination model. Then we will be able to capture this effect. But for simplicity, for the most of the breeding program, we use the simple linear regression model. So we treat this dominance deviation as a noise. So because this part is very small, consider its effects. So when we compare the effects from this noise effects to the breeding effects. So this is how we define this. Any questions here? Okay. All right. And since we have like the average breeding power for allele 1, and we also can calculate the average breeding power for the allele 2. Then because there are two different alleles, we want to see if there's any like difference in terms of the breeding power, right? So we can easily calculate this by take the difference of these two. So this alpha, without any footnote, is equal to the difference between the alpha 1 and alpha 2, and this shows the breeding difference, the difference in terms of the breeding power between these two alleles. And okay, so this is some like the formulas here. So we can easily express the breeding power for A1 allele using this and this. So the simplified formula here. I know, yeah, there's a lot of like confusing terms here, so I'm sorry about this, but yeah, but please take some time to make yourself understand all of this. We're going to use this a lot in the future for calculation, for GWAS analysis, to test the association between any potential loci with the traits of interest. Okay. And okay, so in any genetics or breeding book, you're going to see this term very often, breeding value. So the breeding value means like the breeding power, right? So for example, if a parent has a genotype like this, A1, don't be confused with this. So here, A11 is not equal to A1. A11 means like the genotype for this loci. I could use B1 to represent the genotype for another loci, right? Locus, right? And for this locus, what is the breeding value for this genotype, B1? We still use A1. A means the breeding value. A1 means like the breeding value for this genotype. So A1, A2 means the breeding value for this genotype, B1, B2, the heterozygous. And the A2 means the breeding value for the B2, the third genotype. Okay, so we use A11 to represent the breeding value, which is the additive effects from the combination of two B1 alleles. So this is the breeding value for the combination of the B1 and the B2 and so on. A little bit confusing, I know. The reason why we want to do this, so if you are interested in the future, so if you do some research in the plant breeding or the animal breeding, so this is the term you always use, because if you want to use parental information to predict the genotypic value for the progeny, use the information from the first generation to predict the value, the genotypic value for the next generation, second generation. You can only use the breeding value because this represent the additive parts, right? Additive parts. For the non-additive parts, which is the dominance deviation, I just showed you in the previous slides, that part cannot be captured by by the linear model. So usually we treat that part as the noise. So when you try to do the prediction, the genomic prediction, so you have in the future you're gonna hear about this term a lot. Genomic prediction means like we're gonna use the genomic information from the parental line to predict the performance or the traits of their progeny. So if you want to do this kind of prediction, you can only use the additive parts, which is the breeding value. You cannot consider the dominance deviation because that's the nonlinear part. So usually it cannot be useful for the prediction. So this is why it's the breeding value is important in the genetic breeding. All right. And so in this table just shows you how to associate all these different terms together. So for the genotype like this, that's the frequency in the population, right? If the population is under the Hardy-Weinberg. And all right, so the genotypic value is this. I hope you still remember. Genotype value is, is the phi, which is the phenotypic value minus the midpoint. Yeah. And this is the breeding value derived from here, right? And this is a dominance deviation. That's the non-linear part. This is the linear part or additive part, additive part. So we use A to represent this additive part. And this is not the additive part, non-linear part. We use the dominance deviation, use D. You're gonna see, I'm gonna use these two terms, A or D, to represent the additive or non-additive, means the dominance deviation parts, to describe the different genetic effects. All right, so before we move on, so I'm gonna quickly review some important concepts. Sorry, statistical concepts with you. All right, the linear model. Linear model is means what? Means like if we assume, so linear model actually is a model that can help us to find the linear relationship between two random variables, right? So suppose here we talk about like two random variables. And this example shows like, for example, there's a so if we want to sell the ice cream in the Disneyland, so if you collect enough data, so you want to find if there's association between the daily temperature and the sales of the ice cream in Disneyland. So this is the data you collected, and if you assume there's a linear relationship between the daily temperature and the sales of the ice cream, you can use a linear model to try to fit your data, right? So of course, this data shows a strong association, linear association between these two random variables. Okay, now so in statistics, so first you want to plot the data, and the data will give you the first impression whether your your track is correct or not, your direction is correct or not. So by the first impression, you would say, yeah, there might be a linear association. Then you need to test if this linear association is significant or not, right? So this comes back to our business. So we can form a hypothesis testing to test if this linear association exists between these two random variables. All right. And usually, so in high school or in the college math class, you know how to describe a linear a line, right? A linear line in the coordinator, the two-dimensional coordinator. So usually, if you want to definitively define a line, you have to use two things. One is the intercept. Intercept is the is the cross of this line when x equals to 0, right? The cross between this line and the y-axis, actually, that's the intercept. And then another important term is the slope of the line. So if we want to test the association between these two random variable with a linear line, so you need to test whether this slope equals to 0 or not. Or if we translate this into the statistical language, we want to test if b equals to 0 or not. So if you can use this equation to represent the relationship between these two random variables. So y is the response variable, x is the independent predictor variable, and this is the intercept, and this is the slope, and this is the random error term. So we usually assume this is normally distributed, which mean equals to 0, and the variance like this. Okay, so this is the linear model. And another thing in a linear model is to we need to pay attention is called the least square estimation. So this is a way to estimate the two parameters. So we have two parameters in this model, right? A is the intercept and B is the slope. So how do we estimate these two parameters using our data? The least square estimation is the commonly used way to estimate the parameters, these two parameters for a linear model. And the least square estimation is equivalent to the MLE if we assume the error term is normally distributed, right? Okay, so what is the important thing we need to understand for the least square estimation? So the least square estimation is like this. So if we have the data like this, see the dots in this diagram. So before we can find the best linear model to describe the relationship between x and y based on the data. So there are many ways to draw different lines to summarize the relationship between x and y, right? So we can use a line like this to represent the relationship between x and y, or we can use this line to represent, or we can use this line to represent the relationship, or the line like this to represent the relationship between x and y, right? But which line will be which line is the best fit based on your data? Of course, this line is the best fit, right? So what is the criteria we use to conclude that this line is the best fit for the data? So this is the criteria, least square estimation. So for each line we can calculate. So for example, for each line we can calculate the deviation between each data point with the line, right? So for example, this is a deviation between this point and the line, and the vertical difference, right? So we can calculate the deviation, the difference between each data point with the line. So that's the measure we can use to evaluate, to compare which line is the best fit. All right. So, and because some difference are positive and some difference are negative. So if we just simply add up this difference, absolute the original difference, some positive and the negative will be canceled out. This will not reflect the real deviation from the data point with the fitting line. So instead of using the original data, we use the squared value of each of this deviation, and we try to find the line that can make this squared deviation minimum. So I hope this is clear. So suppose if this is the line and this, so if we want to compare the fitted line with this line, so let's see what happened here. So if we want to compare if the red line is better than the black line, so we need to do the same thing, right? So we calculate the deviation from each data point with this line. So you're gonna see the difference will be much larger between the data points and the red line. So when we compare the least square of these deviations, of course, the red line will give us larger least square as summation compared to the black line, right? So that's the criteria we can use to identify the best fit for your data. I hope this is clear. Any questions here? This is the least square estimation. And so something like this. So for each line, possible line, we just calculate the deviation, the residual between each data point with the line, and we square it and make a summation. And the parameters, either the B or A, will be selected, will be the best estimation, the least square estimation for these two parameters will be selected to minimize this error term. So we call this the error terms. So any questions here? Okay, so we're going to use this in our situation. So, okay, so we're going to use this regression theorem to help us to understand the observed genotypic value for the three genotypes and the breeding value. The breeding value is the best fit for this linear data. Okay. So I don't think we have this diagram in our textbook. I took this useful diagram from another textbook, but yeah, but you can see this in the lecture notes. Sorry. All right. So here, suppose we're talking about a single locus, and this locus has three genotypes: A1A1, A1A2, and A2A2. And this is what we observed. So the black, the solid circle, actually represent the observed genotypic value, which is the 522, 5212, and 511. Okay, and so we understand each genomic value, genotypic value actually consists of the breeding value. Let's say this is 522, right? The breeding value plus the dominance deviation from this genotype, right? And only this part, the breeding part, is the linear part that can be explained by the linear model. So that's why, see, if we use a least square to estimate the best fit line for this three value, we're gonna see like the deviation from each data point from this best fitting line. And all right, so the circle, the open circle on the line is the breeding value. So this additive effects can be well predicted using this linear prediction model. However, there's some part, the difference between each data point with the line, which cannot be explained. That is due to the nonlinear genetic effects, or this is due to the dominance deviation. So yeah, this is a very nice graph. So I hope you can leverage this graph to understand the difference between this important genetic terms. And so this diagram actually use different like axes to show the values for each important genetic terms here. All right, don't worry. So if right now it is a little bit confusing to you, don't worry. Just spend some time to read textbook and read this lecture notes, and so we can. So if you have any questions, we can keep talking about this. So this is very important. I hope everyone of us can understand this, and okay. Excuse me. Any questions so far? Okay, good. All right. So now this is important. Okay. So if we have some value, we need to know how to calculate the expected breeding value for the population, right? So this is what we are comfortable with now. So if we want to calculate the expected breeding value, A is the breeding value, we need to sum, make the summation of each possible outcomes, the breeding value for the genotype A1, B1 and B1 multiplied by its probability, right? The same here and the same here. So if you follow the formula, we can easily calculate this, prove this equals to 0. Yeah, the breeding value, the expected breeding value equals to 0. And the variance of the breeding value equals to this. Why this? Because this is 0. So we have to minus this. The formula is like this, right? There's another term minus this, but this thing is equal to 0. So we just remove this part. So the variance of the breeding value for the population equals to this. And you can do the same thing for the dominance deviation. You calculate the expected value for the dominance deviation using the same formula. So still the expected value for the dominance deviation equals to 0, but the variance of this equals to this. All right, and so based on this, you can see the variance of the genotypic value equals to the sum of these two parts. The variance due to the additive effects and the variance due to the dominance deviation, and you can easily prove this. Okay. All right, let's see. Probably, I think I'm gonna, yeah, let me finish this slide and then I'm gonna stop here because today I think, yeah. So the first 6, I think the first 8 chapters are most important and difficult. Once we are done with the first 8 chapters, for the later on, so that's the application of all these rules and theorems. So we can move a little bit faster, but for the current chapters till like chapter number 8, so we need to move slowly to make sure we are comfortable with all these terms here. All right, because heritability, this is another term we always hear about in genetics, in breeding program, because so when you calculate the heritability, we need to calculate the variance due to the different variability sources. So for example, if we are interested in the variance of the phenotypes, the total variance of the phenotypes, we can decompose this total phenotypic variance into two parts. The first part is the variation due to the genetic effects, and another one is due to the environmental or random error, right? Because this variance due to the environment or random error is cannot be controlled by us. So we don't worry about this part, but we do care about the variance due to the genetic effects. And the variance due to the genetic effects can be further decomposed into two parts. One is the dominant, one is the additive parts, which we can, for which we can make the prediction using the linear model, right? But this part, the dominant deviation part, or the non-additive part, or non-linear part, this part we sometimes we also cannot control. We cannot make the prediction for this part. So that's why we have two versions of the heritability. Heritability actually is the term to describe among the total observed phenotypic variation, what's the proportion that can be explained by the genetic parts, genetic effects. So the broad sense heritability means we use the big H, capital H square. The broad sense heritability means like among the total phenotypic variation, which is the sum of these three parts, right? What is the proportion that can be explained by the genetic parts? Because there are two parts due to the genetics, either the breeding parts, the additive parts, or the non-additive parts. But since the non-additive parts or the dominance deviation sometimes is not controllable, so which we cannot make a good prediction in our prediction or breeding program. So that's why for breeders, for genetic scientists, so we are often using this term, the narrow sense heritability, which is denoted by using the lowercase h square. And if you compare this to, you're going to see this in this formula, the numerator is only, there's only one term in the numerator, which is the variance due to the additive genetic effects. So this is the narrow sense heritability, which is often used in the breeding program. All right, I'm going to stop here today. And I can tell, yeah, there's a lot of like important but difficult terms today. Hopefully, yeah, please, yeah, read the textbook and read the lecture slides again to make sure you can well digest those concepts and the difference among them, because this is very important. All right, so any questions for today's stuff? Maybe it's too confusing for you to ask some questions for now, but it's okay. When you read the stuff, and if you have any questions, we're gonna find a time to discuss. I'm gonna use the rest of the time to go over the practice assignment from last time. Do you agree? Okay. All right. Okay. Oops. Sorry. Stop sharing. Give me a second. Oops. Okay. All right. Let me share this one with you. So can you see my screen? Okay, good. All right. So in the last practice assignment, I gave you two blocks of the R codes. Let me explain this a little bit to you. So hopefully this can help you understand this. And this is important because either for better understanding why we use the bootstrap resampling scheme, right? Another one is like the second one is even more important because I gave you a simpler example to show you how you can use matrix notation to calculate the joint probability if you have a simpler design, the backcross design. So make sure you understand this, and then you can try to expand this to the more complicated situation, the F2 design, and write your own code as a practice. Because in the final exam, very likely for me to give you a problem of the F2 design, and I will ask you to write the code, your own code, R code, to calculate the joint probability of a specific genotype in that design. All right. So let's start from the first one. So the first one, I just suppose this is the sample I got from a single sample I got from experiment. All right, and so if you just simply calculate the average of this, so this gives you like average of this and the standard, the variance. So the variance like this, the variance is relatively large, right? It's large. Why is that? Because if you plot, so this just help you to plot the density distribution of your data. So as you can see, if you plot your data, your sample, so it's not a normal distribution, right? So usually in the statistic, so if the sample is a normally distributed sample, so we can easily, based on the normality assumption, you can easily calculate the confidence interval, the 95 confidence interval using this formula, right? The lower bound of this 95 confidence interval based on the normality will be the mean minus 1.96 times the standard deviation. So this is how we can do this. But as you can see, since this is not a normal distribution, if you use normal distribution calculation to calculate the 95 confidence interval, this will give you a unreasonably large interval. So this interval actually covers the zero, right? From negative to positive. It's too large. The range, the interval range is too large. This is not right because why? Because your data is not normal, but you use the normality assumption to calculate the 95% confidence interval. So this is the case where you need to use the bootstrap. So in the future, in your own experiment, if you get a small sample of small size, if you plot, you can reuse this command to generate the plot like this. If you see your data definitely is not following a normal distribution, then if you need to construct a confidence interval for your sample mean, the resample or bootstrap is a strategy you can use. Okay. What do we do here is like we can generate 100 resamples. For each time, you just use this command. Right? So you generate a resample. What you do is like you just sample from your original sample. SS is your original sample. You sample the same size. So you have in the original sample you have 39 elements. So here you do the resample with the same size, 39. But when you do the sample, you need to make sure that you let the replacement equals to true, which means like each time when you sample a thing from the original sample, you're going to put this thing back and do the second resample, right? So the replacement parameter need to be set as true. So in this case, you can generate 100 resamples, and for each resample, for each of these 100 resample, you can calculate the sample mean, right? And that distribution of the sample mean can give you a better estimation of the 95 confidence interval. So let's look at this. So if you calculate, oops. What is this? Okay, I need to complete this. All right. And so if you calculate the mean of the resample mean, so this will give you something very similar to the original sample mean, right? 5 something. Oh yeah, so this is the mean. So this is the sample mean. And so if you use this quantile to find the empirical lower bound and the upper bound of the 95% confidence interval, you're gonna get a very reasonable range of this 95 confidence interval, right? So if you compare this two, so this is the confidence interval generated using the normal assumption, normality assumption. So this is too large. This confidence interval is too large because you use the incorrect tool to calculate this distribution. Your distribution is not a normal, but you use the normal tool to calculate the confidence interval, which will give you a unreasonable like range. But the bootstrap or the resample scheme can give you a better estimation of the 95% confidence interval. All right, any questions for this? Yeah, hopefully you can use this strategy in the future for your own research program. Right. The second one is, so I gave you a small toy example to show you how you can use your matrix coding to calculate the joint probability. Okay, so here I gave you the transition matrix for from A and B. So I hope you still remember this. So this is the command that we can use. So we just make a matrix and put this matrix to this holder, this random variable. So if you want to see what is in this variable, you just simply like type this and return. It will give you a matrix. So this is the transition matrix, right? 2x2 matrix for the backcross design. And this gives you the non-recombinant, and this gives you the recombinant probability. So the R equals to 0.1, the transition probability from A and B, right? You do the same thing. So you can define another matrix, transition matrix for BC. So because BC may have different genetic distance from the AB. So in this case, I gave you just example. So here, BC is a little bit far removed from each other. So the recombination frequency is a little bit, oh, sorry, it's closer. So the R equals to 0.2, which is greater than 0.2. Sorry, the R equals to 0.2 means like B and C are more removed from each other. Yes. Okay. And that's why you see more frequent recombination during the test cross, right? Okay, so this is how we define the J vector. So J is just the unity vector that can help us facilitate the matrix calculation. So if you cannot understand this now, so go back to this lecture slides to make sure you understand the role of this J matrix or J vector. All right, this is the genotype matrix that we generate to describe because this is a backcross design, right? We have two genotypes, genotype 1 and genotype 2. And you can see the difference here. So the genotype 1 means like we put 1 in this corner, and the genotype 2, we put 1 in this corner, right? Does that make sense? Okay. Now, once you define this, so in the final exam, I'm gonna give you R for the AB and R for the BC. So you have to use this matrix command to generate your own transition matrix. In that case, you need to use 4x4, right? So here, so instead of using the 2x2, you have to generate a 4x4 matrix. So you need to change this to 4. And once you have everything here, so the first one is to calculate the probability of this genotype. So I put this calculation results into this random variable. So this will give you the calculation of the probability of the genotype for A locus is 1, but for the B and the C loci, the genotype are 2. So easily you're going to see a single crossover occurring between A and B, right? There's no crossover between B and C. Does that make sense? So if you do this calculation, you're going to get, this will give you the value. So like this, the probability of having this genotype is like this. So let me explain this to you. So in the regular algebra, so if you, let's say, if you want to calculate 2 times 5 equals to 10, you just use the regular like multiplication notation here. But when you do the matrix calculation, for example, the multiplication using the matrix, you have to use this. So the regular multiplication notation will be surrounded by 2 percentage sign. So when you do this, this will tell R you're going to do the matrix multiplication rather than the regular multiplication. So on the both sides of this sign, you're going to see a matrix and another matrix. Does that make sense? So you use this. So once you want to do the matrix calculation in terms of like the multiplication or division, you have to surround your multiplication or division sign by this 2% sign. So that's why if you want to do the calculation, you see why I put things here, right? So if it is not clear, please do some research online. Just say like in R, what is the notation for the matrix calculation? So it will give you some answer. So I just put this here for your reference. All right, so this is how we calculate this probability, right? I gave you like 3, oops. Yeah, I gave you 3 examples here. So this one, so it's very easy to understand, right? This one gives you the probability of showing genotype 2 at A, locus A, 2 again for B, and 2 again for C. So there's no crossover. So this will give you a much better probability. Do you agree? There's no crossover. So you can see the probability of this genotype is much larger than this one. That makes sense, right? So the same thing here, sorry. This is symmetric. So if you want to calculate the probability of this genotype, still like there's no crossover, right? It will give you the same probability. They are symmetric. Does that make sense to you? Okay, so I'm done with this, with today's lecture. So any questions, either for the practice assignment or for today's lecture? All right, I hope you enjoy today's lecture. Yes, I agree. It's a little bit like confusing and complicated, and we should have used some different notation to represent different like terms. But unfortunately, in that textbook, so there's some like confusion in using those like letters. So maybe in the future, Dr. Xu can consider publishing another edition to use like more clearly like defined like notations to help you. But yeah, it's fun to study this stuff, and hopefully you can learn some useful tools, things for your own research in the future. All right, thank you everyone. If you do not have questions for now, so I will see you next week. And I'm gonna think about some other like assignment practice for you. So to summarize our this week's lecture. All right, bye. See you next time.
Thank you. Bye-bye.
Bye-bye.